Hello everyone, my name is Khan Amatai,
I'm Madeline Lee.
and we're hired sedimentation bottom geometry. So what is it that we do? We are currently researching the sedimentation tank and sedimentation process in Omkara Plant. This process is currently the part that takes up the most amount of space and hence is the most costly part of the Omkara Plant. We are trying to research methods to increase the flow rate through the sedimentation tank to hence reduce the space required and hence also decrease the cost. This is the current lab apparatus that we're using to research. We're utilizing 3 water pumps, one to push water, one to dose coagulate, and one to dose clay. We're using a flocculator, which is coiled tubing, which mimics the flocculator in the Omkara plant, and a sedimentation tank, which we will further discuss. This is what our sedimentation tank looks like and how it mimics the Omkara plant. The recirculator is a vertical section which mimics the flock blanket area in the Omkara plant. The tube settler is a slanted portion of the tube, which is meant to mimic the sedimentation plate in the Omkara plant. And the flock weir is used to remove an excess amount of flocks from the flock blanket to keep it at a constant size and constant density. So what is the problem that we're trying to research and trying to fix? A phenomenon called flock blanket decay is something that has been occurring in the past several semesters. This is denoted by all of these graphs. As you can see, as the experiment goes on, the effluent turbidity starts to increase at an exponential rate. This is what we're calling flock blanket decay, as it indicates the flock blanket is working less efficient than it initially does.
So the purpose of our sub-team is to redesign the bottom of the sedimentation tank to ensure proper recycling of flocks to make a more efficient flock blanket, and also to avoid the settling of flocks within the recirculator, because if the flocks settle all to the bottom, it makes it very difficult to clean because these flocks can only be removed manually. And so here is some previous work done by the HRS team of summer 2018. It is a drilled filter insert with a regular conical shape, and you can see that here it failed because you can see there's a buildup of flocks at the bottom, which is exactly what we're trying to avoid. So here are some current hypotheses, and Monroe proposed an analogy to explain why the previous model didn't work, and it's the analogy of a group hug. If you imagine a bunch of people in a group hug with their arms linked together and they try to take a step forward, they won't go anywhere. So if you apply that to flocks, if the flocks are locked together in a ring, they won't be able to take a step forward, and that's why there's settling at the bottom. So this model, the symmetrical Omkara plant design, will prevent the group hug of flocks, and these slope planes redirect flocks back down into the center. And here's our printed insert that we sent to the rapid prototyping lab, and we modified it to make a circular bottom. One of our other hypotheses is an off-center cone, where you can see that in this tube settler that the bottom is sliced, and because the bottom is sloped, it'll also allow redirect flocks down and avoid group hugs. This is our 3D model. And here's a picture of our printed model. You can't really see here, but the sides are sloped to also prevent group hugs.
So once we have the 3D printed designs, we decided to try and get a baseline test. After running an experiment at 3 millimeters per second upflow velocity, we quickly realized that we're getting significantly different results than that obtained by previous higher sedimentation teams. In this graph, although it looks like the flock blanket decayed extremely rapidly, our y-axis is extremely zoomed in compared to the initial graph, with the maximum being 12 as opposed to 100. This means that after 21 hours of running, our flock blanket decayed at a linear as opposed to exponential decay, and even after 21 hours, the effluent turbidity was still below 10 NTU. Because our team was getting this result extremely different to the higher sedimentation teams previously, we decided to run an experiment at 2 millimeters per second, as previous semesters were not obtaining a flock blanket at this outflow whatsoever.
And we also wanted to run another baseline at a 2 millimeter per second upflow velocity, and we were able to create a stable flock blanket with a low effluent turbidity of 2 to 4 NTU, and this contradicts the summer of 2018 HRS team's results, where they weren't able to get a flock blanket at all at this upflow velocity, but we attributed the difference to the difference in flocculators. And so we ran another experiment using the HRS 2018's flocculator versus ours at a 2 millimeter per second upflow velocity, and you can see that there isn't much of a difference between the two, and that we were able to get a stable flock blanket at both using both flocculators. So this confirms that the discrepancy of success of acquiring a flock blanket at 2 millimeter per second velocity upflow is not caused by a difference in flocculators.
So once we had run the experiment comparing the flocculators, and we know it's no longer attributed to the flocculator, we decided to see what actually was going on in the sedimentation tank. As in previous experiments, we either ran out of clay or coagulant before we got back into the lab, and hence never really got to see what was occurring in the sedimentation tank. After running the experiment and coming in after 24 hours to see what was going on, we noticed that there was really dense buildup of flocks at the bottom. From here below, the flocks build up a blanket that was very solid, was almost solid-like, and above it we had a very dense flock blanket of suspended flocks. Because the bottom is the majority of the flock blanket was solid-like, we believe that this is less dependent on upflow velocity as it's no longer suspended, and hence is more stable than the suspended flock blanket that we had above. However, flock blanket buildup is not ideal, and Maddie will touch upon that.
Overall, we found two main discrepancies with our experiments this semester and the summer's experiments. And one of the discrepancies was that we're able to produce stable flock blankets at an upflow velocity of 2 millimeters per second with a low effluent turbidity of 2 to 4 NTU. And we were also able to produce stable flock blankets at a 3 millimeter per second upflow velocity. And the difference was that we found a linear increase in effluent turbidity as opposed to an exponential increase in effluent turbidity. And we also found that the buildup of flocks contributes to the stability of the flock blanket. And the buildup by nature, as Kanha mentioned, is a dense solid layer that does not decay. But flock buildup is not desirable because it increases required maintenance time and downtime for the system, since flocks and the dense layer can only be removed manually.
So what are the next steps? The first next step is to test whether the buildup occurs at 3 millimeters per second. Due to some complications with the lab apparatus, we were not able to test this at the end of the semester, and hence we would like to see if it occurs at 3 millimeters per second, to what extent, and why we're seeing a linear increase as opposed to no increase like we did at 2 millimeters per second. The next would also be to test different coagulant doses. At the start of the presentation, I showed you previous high-rate sedimentations experiments testing the difference in effluent turbidity with different coagulant doses, and as we are obtaining significantly different data to previous semesters, it would be interesting and quite necessary to see whether the different coagulant doses will have a different result. The next would also be to test the 3D printed designs that we made at the start of the semester. Although flock buildup was giving us a very stable flock blanket, we do want to avoid it. We want to see that if these 3D printed designs were able to produce an equally stable and an equally efficient flock blanket without having the solid-like dense layer which has to be removed manually. And the last step is to determine whether buildup could actually be occurring at Omkara plants, but we just don't know about it, as the only way we're able to actually see what's going on in the sedimentation tanks in the plants is from above. In our experiment, we saw that we were getting a flock blanket buildup at the bottom, but at the top we were getting a really good, really dense flock blanket. It is possible that this could be occurring at the Omkara plants, and finding out whether flock blanket buildup occurs there could potentially mean that we were wrong about flock buildup requiring extra maintenance and extra downtime. If you have any other questions or recommendations, feel free to